So hi, I'm Thomas Burton. I'm a PhD student at the I'm a PhD student at the University of Oxford, and today I'm going to be talking about our work on smartphone model fingerprinting using Wi-Fi radiation patterns. So this is a work by myself and my supervisor. Yeah, so let's get started. My PhD is looking into the security implications of radiation patterns. I'll explain exactly what radiation patterns are in a moment if you're not familiar. But our goal is to demonstrate the feasibility of using radiation patterns for device identification or device fingerprinting, whichever one you want to call it. The first thing I'm going to discuss is determining what level of identification is possible using radiation patterns from smartphones. Then I'm going to be talking about how you can actually do identification like this in the real world, because this is actually quite challenging. Then I'm going to discuss the security of this method. So can someone easily spoof someone's identity? So I'm first going to go over the necessary background knowledge. So there's 3 parts here, each quite brief. So first of all, those who aren't familiar with received signal strength, this is a pretty fundamental part of what I'm looking at. And RSS, which is received signal strength, is a measure of power of a received signal when it's transmitted, by the receiver from when it's transmitted by a transmitter. This is measured in watts or milliwatts or decimal milliwatts in some cases. We normally just use decimal milliwatts, but there's other ways you can measure this. The units you can use. And conventionally, RSS is used for localization and problems of that nature. But as I'll explain in a minute, it is also useful for fingerprinting. There we go. The next background element is existing wireless device fingerprinting. So you can broadly categorize this into 2 groups. So we have unique device fingerprinting, where the aim is to distinguish individual devices. So every device is unique in some way. So this can be done very easily by just using some form of ID, like an IP address or a MAC address. But this can be very easily spoofed. So we can supplement this by using different cryptographic methods, but these have problems to do with power usage in low power devices and kind of initial key sharing problems. So it's not always ideal. Then there are 2 types. If we want to look at the actual properties of a signal or properties that we're able to measure, we can look at 2 kind of different methods. So we can have location independent techniques or location independent techniques. And so with the idea of location independent techniques, wherever a transmitter is that you're trying to identify, the location of it shouldn't matter. So we can use several different techniques for that. So we can use transient-based techniques, modulation-based techniques, and spectral-based techniques. And these generally have a very high accuracy, but are quite difficult to deploy because you need very specialist hardware in order to measure kind of very fundamental properties of the wave signal. It's not ideal if you're trying to add identification to an already existing network, for example. Location-dependent techniques rely on this idea that you can use location as a proxy for identity. So if we have a desktop computer that's connected to a wireless network, if it's just in a position, if we have a set of receivers set up around the place, we can measure the received signal strength. And with several of these measurements, we have a kind of fingerprint. And when we then compare different devices, this fingerprint should ideally be unique based on where the position is. And so there's received signal strength techniques for doing this, and also using channel state information. The next kind of category we can have, I forgot to mention the problem with location independent techniques is they don't really work in a mobile context. So that's an issue. So the next kind of category is device type fingerprinting. And unlike before, where we were just trying to identify each device completely uniquely, device type fingerprinting aims to kind of classify a device into groups based on some element of their hardware or software. So we could try and categorize iPhones or a particular brand of access points, something like that. And this is normally based on the behavioral characteristics of a particular device. So how does it cope when a particular packet with a very particularly constructed preamble is presented to them? Do they reject the packet? Do they accept the packet without any problems? Those kinds of things for packet manipulation. We can also do kind of fancy techniques to do with traffic analysis and timing of particular packets. So if an access point receives a series of packets, particular vendor implementations might mean that the packets, when they're retransmitted, the gaps between the packets are shifted a set amount. So but the problem with these techniques is that they're potentially limiting in some degree, because if we're basing it on a particular behavior of software or hardware, then at least in the hardware case, there's not that many different vendor implementations available. It could be possible, this isn't exactly true, but it could be possible that Apple put all the same wireless chips into their iPhones, and therefore all iPhones look the same. And maybe we want something a bit more precise than that. We want smaller groups. So finally, the third background area I'm going to talk about is radiation patterns, and this is very important. So what is a radiation pattern? So antennas don't radiate power uniformly. This is very well known and acknowledged. It's physically impossible. So even in settings where we would like uniform power distribution, for example, in mobile communications, it might be useful if your phone, no matter the orientation, receives the same signal strength. There is some ununiformity with the pattern. So we can represent radiation patterns in several different ways. So we use directivity, kind of a similar idea to gain, but gain, for those familiar with it, gain includes directivity and also some electrical efficiency calculations. So, but directivity is the ratio of the radiation intensity in a given direction from the antenna to the radiation intensity averaged over all directions. So if you look at the slide, this is just a 2D measurement from of a radiation pattern from a Samsung A50 smartphone. And as we can see, in some directions, we have a higher intensity in some, we have a high directivity in some directions. And on this particular way of representing it, the further out the line is, the higher the directivity. And in this graph, it's shown in the units is dBi, which is just a measure relative to an isotropic antenna, which would be uniform in all directions. So for this concept to work, the idea of using radiation patterns for fingerprinting smartphones, there's sort of two properties that we need. We need uniqueness, whether that's individual device uniqueness or particular models of device uniqueness. And then we also need repeatability, because we don't want to measure a radiation pattern, then go away and come back the next day and it'd be a completely different pattern. That just wouldn't mean this technique doesn't work. And beamform, there's a trend towards beamforming, which means that the patterns do change to some degree. And while that may be a problem in some settings, for a lot of the current generation of smartphones and general devices, thinking of IoT devices and other legacy devices, beamforming isn't an issue. So our first step was to look at both of these properties. So we measured a series of patterns. We ended up having 6 phones, and we measured the patterns, and we wanted to verify that these properties existed. And we wanted to determine what type of fingerprinting could be performed, or what was the most promising. So, as I said, we took 6 smartphones. Unfortunately, we weren't able to get more. It would have been nice to be able to borrow phones from other people in the research group in the office and whatnot, but COVID restrictions prevented that. So we measured multiple 2D patterns. We measured 3 2D patterns from each device on different days. So we were showing that this was repeatable. And we calculated the cross correlation between the different patterns. So from this, we learned that devices of the same type tend to have a very high correlation, and other devices have a very low correlation. So this indicates the significant difference between models. But it also demonstrates that repeatability holds, and the uniqueness seems to apply to models. So those are the two properties that are important. Although limited, this suggests that device type fingerprinting is possible, but unique device fingerprinting is maybe less possible. Maybe not possible. So disadvantage is we can't uniquely identify different devices, but the advantage is we can identify models without having to enroll each type of device, because we can just enroll one of that device, and then we know the pattern for that model of a smartphone. And to be clear, by model I mean we have a manufacturer, and then obviously under that we have different models. So we have iPhones, but we also have iPhone 10s, 6S, 5S, and they produce different patterns. So building on this, we want to create a fingerprinting method that we can use. Our kind of system model, we have several components. So first of all, we have an unknown transmitting device. A transmitting device of an unknown type, T. We have an environment where there's multiple receivers set up that can measure received signal strength. We then have a calculation server, which is separate. It's connected by wires to different receivers. And this has several important bits of data on it. So it has a receiver position database, a reference pattern database. So the reference patterns are just all the different patterns that we may want to, all the different patterns of phones we may want to identify. Then for those who are familiar with RSS localization techniques, we start off by performing a site survey where we move a reference transmitter around an environment and take RSS samples. And so the site survey data is held by the calculation server. And as I've already mentioned, we have a reference transmitter, which is the tref. So from now on in my descriptions, I'm just going to use 4 receivers, 3 reference patterns, and 2D environments and patterns as an example. But this applies for any number of receivers, any number of reference patterns, and also applies in the 3D environment and for 3D patterns, although the calculations become slightly more complicated. Okay. So as I've already mentioned before, we know that smartphone radiation patterns have the 2 desired properties that we want. So how can we leverage this for identification? So intuitively, we can see that if we have a set of directivity point measurements for a particular device, then we can attempt to match this to a group of patterns. So on the slide, we have an unknown device. We have an estimate, or we have a known directivity in different directions, and we just try different orientations to match it up to a list of potential patterns in a database. Now, this is more difficult in practice, obviously. First of all, directivity is not a property you can just measure. We need to do some calculations in order to estimate it. Secondly, because we're dealing with RSS, we have the problem of fast fading, which means there'll be some noise in our measurements. Finally, it's possible there may be close matches on multiple patterns because we have a limited number of receivers. If we had an infinite number of receivers, we could just create the pattern. We could very accurately match it to one of the patterns, but we have a limited number of receivers because in realistic settings, there's only so many receivers you can have. And this issue of multiple close matches only gets worse with 3D patterns because obviously there's more freedom to try different orientations and rotate the patterns, so we have to match it up to more. So first of all, what we need is some way to estimate the directivity remotely, and then we need to repeat this process many times. So remotely estimating directivity, we first look at that. So we model RSS as equation 1, which is at a particular location. RSS is a combination of transmission power, TPX, directivity of the transmitter in the direction of the receiver, so that's DT, and finally the effects of the environment. And this includes things like path loss, slow fading, directivity of the receiver, but importantly, for a particular location, E is constant. This allows us to compare two different receivers at the same two different transmitters at the same location. So a reference transmitter and then a transmitter that of an unknown type. So on the left-hand side, we kind of show a quick example of this. So we have at the top, we have a reference transmitter. It has a known radiation pattern, therefore a known directivity, and we can use an equation to directly compare this to the transmitter at the bottom, which is unknown, has an unknown directivity, and yeah, we can compare those with that equation too. We can then start in using more receivers, and this allows us to create a system of equations that we can compare. So for each receiver, we have an equation with one side being the reference transmitter and one side being the unknown transmitter. So how can we use this when we have multiple patterns and want to find the best match? So as I've just said, we can have a system. We can create a system of equations, and we can create one for each possible pattern in an attempt to identify the best location and orientation for a device. So we have our system. So we have multiple equations. We have multiple instances of two, one for each receiver, and we basically want to, by trying different patterns, trying different locations, and trying different orientations, we try and minimize the difference between the reference transmitter side of the equation and the unknown transmitter side of the equation. In practice, this when you start doing this, it actually requires some matrix transformations in order to deal with the direction to the different receivers. I'm not going to cover this now, but that's covered in the paper. It's a fairly trivial process, although it gets slightly more difficult for 3D examples. Now, the exact method used to do this can be varied. We use a brute force of just searching the entire search space with some optimizations, and there's actually quite a lot of optimizations you can do, which I'll discuss in a moment. But so for each potential radiation pattern, sorry, each reference pattern, you perform this process, and we try and identify a location and orientation that best matches based on the measurements that we've taken. And we then, for each of these patterns, we reverse this process and then we calculate the directivity. And we store this in a pattern database. And as you can see on the slide, we represent this by just plotting the red dots in their best matching position on the three patterns. So to then deal with the issue of fast fading and potentially slow fading, if that's temporary, we do this many, many times. And eventually we fill a large proportion of each reference pattern. And any time we can try and we can ask for the system to classify the device, and we just take the device that has the lowest difference between all the red points and the actual pattern line, and so we take the lowest estimate. Now, the problem with this is, because we can do this at any time, clearly if we don't have many points or points cover a very small area of the pattern, the accuracy is going to be fairly low. So we need some form of coverage metric. So the coverage metric, what we want is to have a situation where a high coverage metric implies a high accuracy, and I'll explain in my evaluation in a second how that holds. But so the way we produce our coverage metric, because importantly we're using arrays as a data storage type, so we essentially have bins, so it's kind of difficult to there's no trivial way you can just measure kind of the coverage of all these patterns. But so our way of measuring how much the pattern is covered is we split the pattern into wedges of omega, progressively smaller values of omega, and we find the smallest omega we can get where at least W% of the points fall into each wedge. And now the W is configurable, and you can tune it to kind of get exactly the properties you want. And then we normalize this value and invert it just so it's between 0 and 1 to give an idea of how the coverage that's given. And yeah, so then that outputs a coverage metric. So when we do classification, we get the output of the device type estimate and also a coverage metric to go along with it. There we go. So it's a very quick summary of this process. We receive a packet, we process the RSS data from the multiple receivers, we do those calculations I discussed, and we keep repeating that process until we want to perform the classification, at which point we look at the pattern database, we see which has the lowest error, and that gets output along with the coverage metric for all of the patterns. So there's some optimizations that can be performed. Given this is a brute force search that we're essentially proposing, this is fairly important. So first of all, a lot of the matrix transformations can be pre-calculated, and this means we don't have to do any trigonometric functions or anything at runtime. We can also store patterns as arrays, which is a lot more efficient than storing patterns as equations, which can end up having to have huge numbers of exponential calculations done, exponent calculations done. Then with very large numbers of reference patterns, we can start culling kind of the poor matching ones after either a set time or a set number of packets. And finally, we can start applying some movement constraints or do some initial inaccurate localization process, as we don't really want to be searching the entire possible space of locations if we can do some sort of step to cut down on that. So the limitation of this approach is that we do assume that E is constant. Now, obviously, this may not be true. We can get around some of these issues by doing multiple site surveys with objects in different positions. If they're moving around, for example, if we have a door that's open and closing all the time, then you can deal with that by just doing a site survey with it open and a site survey with it shut. And our hope is that temporary changes are dealt with over the period of classification. So ideally, we don't want to just get 20 packets and then try and classify the device. We want, you know, hundreds or thousands. So the key thing that we wanted to show in our evaluation was that the coverage metric does imply a high classification accuracy. So we did this with simulations. We simulated a 20 by 20 meter environment. We simulated the site survey. Then we used the patterns we already collected as various transmitter patterns, and we randomly moved the transmitter through an environment and had the receivers in set positions, and the transmitter rotated in various things. And we measured the false positive and true positive rates and plot that as a receiver operating characteristic curve. And this clearly demonstrated that with higher coverage metrics, we got an improved accuracy. So we're confident that the coverage metric is effective. We also looked at issue with the number of receivers, and we found that the true positive rate definitely ramped up a lot faster with more receivers, as we'd expect. And we did a similar thing with pattern fidelity. So we looked at if we have larger or smaller resolutions of the pattern, what effect that had on the true positive rates. And again, we found that with higher resolution patterns, that improved the number of packets, the reduced number of packets required to get a high true positive rate. So the important thing that we then looked at was how easy it is to trick the system. So we considered a scenario, kind of bring your own device to work scenario where people could bring their own smartphones, and the goal of the attacker is to trick the system into thinking a device that's not on an allowed list is on a device, is a device on the list. So we just arbitrarily came up with a device list. Allowed devices, sorry. So we don't make any guarantees of location or orientation from our systems. So we didn't analyze those in our security analysis. And so for an attacker to be successful, the attacker must find or produce a pattern that matches endpoints on the pattern on a pattern from the allowed list where n is the number of receivers, and we allow some tolerance. So we came up with two attack methods. So we have first of all a misclassification attack, and the idea, this is the simplest form of the attack, and the idea of this is an attacker would try and orientate himself such that his transmissions would be mistaken for transmissions from from a device on the device list. Clearly we can see on the diagram on the right, we have two different measured patterns, and as you can see clearly there are points of overlap, and this means that at a particular location, the device can pretend to be another device. However, we also need to consider that the attacker doesn't have control over the receivers. So if we increase the number of receivers, it becomes more and more difficult to find appropriate matches. And also, the device will still have a strong match to the actual device model that they actually are, assuming that they are in the pattern database. So, and this becomes even more difficult if some of the receivers are unknown. So this kind of attack is very difficult and not particularly effective. The next attack method we came up with was pattern modification attack, and for this we looked at and the idea of this is the attacker modifies their pattern to match another pattern, and we found that actually modifying a pattern is fairly difficult, as the effect of placing kind of blocking material around a smartphone has a kind of unpredictable effect, although it's deterministic. So it's actually very difficult to create a match. So counterintuitively, we found actually the best method for a pattern modification attack is to try and make your pattern as dissimilar to every other device as possible. The more peaks and troughs you're able to create with your pattern means that you have more potential overlaps, and therefore it's easier to potentially find matches. However, when we did a few simulations, we found this is still not very effective because the coverage metric requirement forces the device to have far too many matches than we were able to reasonably create with 2D patterns in this case. So to conclude, we found that the radius patterns can potentially be used for device type fingerprinting. We proposed a method, and we found that the coverage metric that we produced ended up being the greatest barrier for any attacker to spoof the identity of another device. So thank you. I look forward to